today I'll be presenting on the epsilon delta definition of continuity. This presentation is going to consist of 3 parts. So the first is going to cover historical background and importance of the definition. The second will cover the proof of the definition. And the third will cover a real-life application of it. So here, basically, we have some historical facts about the definition of continuity. The early ideas of continuity were proposed by Euclid and Archimedes, the 2 mathematicians. And later on, Newton and Leibniz began to intuitively use limits and continuity, but there was no formal definition for it yet. And in the 18th century, Euler and Lagrange began to use calculus more frequently. However, because there was no proper definition for continuity at the time, there were a lot of issues and inconsistencies met. And later on, in 1821, Cauchy came up with this definition of continuity where he defined a function as continuous if a small changes in its input result in small changes in its output. And it was not as precise as the modern one that we have today, but it laid the foundations for the modern one. So here we have the definition that we know today, attributed to Weierstrass, and it says that a function f is continuous at a point x equals c if for every positive epsilon there exists a positive delta, such as if the absolute value of x minus c is greater than 0 and less than delta, then the absolute value of fx minus fc is less than epsilon. And it seems like a mouthful, but basically it's saying that a small change in the function's input, in this case x, will result in a small change in the function's output, which is fx. So a small change in x will result in a small change in fx. And later on in the 20th century, this epsilon delta definition became fundamental. It became very important in calculus and real analysis. And until today, it has it takes a big part in theoretical mathematics and applications in various fields such as science, engineering, and beyond. And so here we have the definition of continuity in multi-dimensions. And so here we say that D is a subset of Rn, and x0 is a limit point of D, and we have the function g. Basically, there are 2 ways to express the continuity of g at x0. And the first one is saying that if xk is a sequence of points in D converging to x0, the sequence gxk converges to gx0. The second one is similar to the definition that we've seen just now. It says that for any epsilon bigger than 0, there is a delta bigger than 0, such that if the point x is in D and the norm of x minus x0 is less than delta, then the norm of gx minus gx0 is less than epsilon. And here we note that the point x now has become a vector because we are in higher dimensions. We're dealing with more than one variable. It's the same with g also. And the norm is always positive. So you can see that x minus x0 is less than delta. We don't need to specify that it's that it's bigger than 0 as in the previous definition. So next, we're going to move on to a proof of this definition. Right, so here we're going to move on to a proof of the definition. And basically, what we want to do is show that these 2 statements imply each other. So first, we want to prove the forward direction. We want to show that the first statement will imply the second. So to start off, we consider a sequence xk within D that converges to x0. And since x0 is a limit point of D, we do not include it in the region where xk is. And so our goal is to show that gxk, the sequence gxk, converges to gx0. So to start off, we want to assume that the second statement holds. And then it gives rise to point number 2, which says that given any epsilon bigger than 0, there exists a delta bigger than 0, such that for any x in D with x minus x naught less than delta, we have gx minus gx naught less than epsilon. And so to understand this, basically, given any epsilon bigger than 0, it's saying that for any small positive number epsilon, this epsilon decides how close we want gx to be to gx naught. And for the delta bigger than 0, it's saying for this particular epsilon, there is a corresponding small positive number delta that represents how close x needs to be to x naught in order for gx to be within epsilon distance of gx naught. And then for any x in D with x minus x naught less than delta, we have gx minus gx naught less than epsilon. Is basically saying that if x is a point in D such that the distance between x and x naught is less than delta, then the distance between gx and gx naught will be less than epsilon. And so to point number 3, since the sequence xk converges to x naught, there exists an integer n such that for all k bigger than or equal to n, xk minus x naught is less than delta. So since xk converges to x naught, is basically saying that the sequence xk gets arbitrarily close to x naught as k increases. And the rest of it is saying that because xk converges to x naught, we can find a specific point in the sequence. In this case, let's call it n, that after which every term xk is within epsilon distance of x naught. And so moving on, we have the next few points, which says that by definition, the points xk are in D slash x naught. So the sequence xk consists of points within the set D that explicitly excludes the point x naught. And so in point number 5, it says for all k bigger than or equal to n, gxk minus gx naught is less than epsilon. So because the points xk are within delta distance of x naught, as we established earlier, now it's saying that the difference gxk minus gx naught is less than epsilon, thanks to the condition that we assumed earlier. And therefore, in point number 6, we get for any epsilon bigger than 0, there exists an integer n such that for all k bigger than or equal to n, gxk minus gx naught is less than epsilon. So basically, they are saying that no matter how small epsilon is, there is always a point in the sequence, in this case n, such that after which all the subsequent terms are such that the distance gxk minus gx naught is always less than epsilon. And therefore, we have already, this implies that the sequence gxk converges to gx naught. Because the values of gxk get arbitrarily close to gx naught after a certain point in the sequence. Therefore, it's saying that the original statement, the first statement, is true, and it proves that the function g is continuous at x naught. We're going to use something called contraposition, which we have learned before. And basically, we want to assume that the second statement is false, and therefore, the first statement is also false. And so to do that, we're going to apply De Morgan's law to the second statement. And basically, if we recall what De Morgan's law does, it changes the false to exist. So here we get the following statement. Seems very complicated, but in point 2, it basically explains that it's saying that there exists an epsilon bigger than 0, so that for every delta bigger than 0, there is a point x in D slash x naught with the distance x minus x naught less than delta, but the distance gx minus gx naught is bigger than or equals to epsilon. As opposed to the previous one, we recall. So basically, it's saying that there is some epsilon bigger than 0 such that no matter how small we choose delta, we can always find a point x in d/x0, which is within delta distance of x0, but the function values gx minus gx0 will differ by at least epsilon distance. So not less than epsilon, at least epsilon. So bigger than or equal to epsilon. And so for point 3, what we can do is construct a sequence xk in d/x0 as follows. So for each positive integer k, there exists a point xk in d/x0 such that xk minus x0 is less than 1 over k, but gxk minus gx0 is bigger than or equal to epsilon. So it's saying that there exists an epsilon bigger than 0, such that for every delta bigger than 0, there is a point x in d/x0, such that the distance between xk and x0 is less than 1 over k, but the distance between gxk minus gx0 is bigger than or equal to epsilon. And so here you can see that we choose the delta to be 1 over k, and we construct a sequence xk where each xk satisfies xk minus x0 is less than 1 over k. So xk gets arbitrarily close to x0 as k increases. And despite xk converging to x0, we have gxk minus gx0 bigger than epsilon for every k. And then here we have the rest of the points here. It says that the sequence xk is a sequence in d/x0 such that xk minus x0 is less than 1 over k, as we have constructed the sequence. But here we say that as k approaches infinity, the distance xk minus x0 approaches 0, because the limit of 1 over k equals to 0. That means that the sequence xk converges to x0. And given that gxk minus gx0 is bigger than or equal to epsilon for all positive integers k, the sequence gxk cannot converge to gx0. So despite the points xk getting arbitrarily close to x0, the function values gxk remain at least epsilon distance away from gx0 for all k. And thus the sequence gxk cannot converge to gx0. So we have basically proved that there is a sequence xk in d/x0 that converges to x0, but the corresponding sequence gxk does not converge to gx0. So basically we're proving that the first statement is false, because we assume that the second statement was false, and from there we showed that the first statement was false. And so in other words, if you reverse it around, you're going to say that the first statement is true means that the second statement is true means that the first statement is also true. We can consider the act of playing the piano as a multi-dimensional function. And so if you consider the input, we can say that the input is the speed and velocity, the position and the velocity of my fingers on the keys, timing, and dynamics. The output, fx, we can take to be the sound produced, including the pitch, the volume, as well as the rhythm. And so we can say that my performance is continuous if small changes in the input result in small changes in my output. So basically, small changes in my actions will result in small changes in the sound produced. So for example, let's if we focus on one specific chord or note, and for example, let's say this, and I can vary my adjustments in my finger position, the pressure and the timing, so that it can cause equally small changes in the volume, the pitch, and the rhythm. So basically, if I take the small variation in my actions to be delta, and the desired the sound produced to be epsilon, a small change in the speed of which I press the key will not affect the sound produced much. So for example, in pitch, there is a certain precision in the finger placement called delta. So if you look here, obviously, if I vary my position enough, you will see that eventually I'm going to hit another key in front of me, or I'm going to hit another key to the back of me. So if I vary enough, I'm going to hit this key. If I vary enough, I'm also going to hit this key. So basically, the interval, you can take the interval, the length of one key to be delta, and I have to stay within this delta in order for the pitch to not change. If I go beyond it, I'm going to change the pitch. If I go beyond this. So basically, they're saying if my finger positions changes slightly, but still stays within delta, the resulting pitch is also going to stay within epsilon. It's not going to change. So I vary, the pitch stays the same. It also is the same for dynamics. So if we take the force applied to the keys, and we say that I have to vary this such that it is within delta, that if I make the change in the key small enough, you actually won't be able to hear the change in volume. So if it's small enough, you won't actually be able to hear any change. But if I make it larger than delta, you can actually hear a difference. So basically, it's saying that if the force applied to the key is within delta, the volume of the note also will stay within a certain range. It's the same goes for timing also. There is a certain precision at which I can press the key so that you won't be able to detect a big change in the rhythm. So if I press and I vary it very small within delta, you won't be able to hear much change in the rhythm. But if I go beyond delta, you can actually hear. So the rhythm, you can actually hear the change in the rhythm more. So basically, if I only change the timing of the key press slightly, the rhythm also will stay within a certain range. So the change in rhythm will also be less than epsilon. And so basically, if I were playing and you imagine a graph, say of my volume, so you will, if my movements in my variations are small enough so that the performance is smooth and continuous, you won't see many big jumps in the graph. You won't see like the volume jumping from here to here, here to here. The volume will be, it will stay within a certain range. It won't be just jumping all over the place. So yeah, you can take that to be a continuous performance because small variations in the force in which I press the key will result in small variations in the volume of the sound produced. So yeah, that's it. Thank you for listening.